A random variable takes numerical values that describe the outcomes of some chance process. They can be discrete or continuous, but today we're going to talk about discrete random variables. A discrete random variable x takes a fixed set of values with gaps in between. The probability distribution must have outcome probabilities that are between 0 and 1 and that add up to 1. A discrete random variable has values which are obtained by counting. It differs from a continuous random variable because the values for a continuous random variable are obtained by measuring. An example problem could be find the cumulative distribution of the probability of getting less than 2 heads when 3 coins are tossed at the same time. So you would write out the sample space, so all the outcomes that are possible, and here we have 8, and because half of the outcomes have less than 2 heads, the cumulative distribution for getting less than 2 heads is 1/2. A common mistake could be that it's easy to miscount the number of heads/tails for an outcome or repeat an outcome. Make sure to double check your sample space.
Conditions to classify a distribution as binomial follow this acronym called BINS. So B is binary, and what that means is that there should be a success and a failure that can be identified. I stands for independent, which means that each trial should be independent of the other trials. N stands for the number of trials, which means that there needs to be a fixed number of trials. And S stands for success, which means there needs to be the same probability of success for each trial. So if you discover that a binomial distribution is applicable, the mean is NP, and the standard deviation is square root of NP times 1 minus P, where N equals the number of trials, and P equals the probability of success on any one trial. Now moving on to probability calculations by hand. So we have one formula that we can use when we are trying to get the probability that X equals K, like a certain value happens. If you want to take an easier step, you can do it using calculator functions. Something to keep in mind for using binom CDF is this complement rule. The calculator will only calculate less than or equal to. So these are the complements of each of the corresponding things, and you would have to do 1 minus that in the calculator. So lastly, when to classify a binomial distribution as normal is when NP and N times 1 minus P is greater than or equal to 10. So N must be large enough for NP and N times 1 minus P to be at least 10. And if that's true, the mean of the sampling distribution of P hat and X bar are shown here, and the standard deviation of P hat and X bar is shown here. Here is an example problem from the AP Stats book, problem R6.6. So you would define X with N equals 8 and P equals 0.2. We want the probability that none of the candies are orange, so P of X equals 0. So we can plug it into the formula that I mentioned earlier, equals that probability, and because this probability is not that small, it would not be surprising to get no orange M&Ms in a sample size of 8, or you could choose to use your calculator with binom PDF. For common mistakes, when using the calculator functions, pay attention to whether you are using binom PDF or binom CDF. Binom PDF is used when you are calculating the probability that X equals that number, whereas binom CDF is when you are calculating the probability that X is either less than, greater than, less than or equal to, or greater than or equal to.
For expected value, it describes the long run average outcome, and it's pretty much the mean. And the formula is the summation of xi times by pi. So for example, this outcome has plus 5,000 and then minus 10,000, and each they have their own unique probability. So to find the expected outcome, or the expected value, you take 5,000 times by 0.8 minus 10,000 times by 0.2, and then that's equal to 2,000. And then you have to find the standard deviation. To do that, first you find the variance, and that's equal to the standard deviation squared due to the summation of x minus the mean squared times by the probability. To find the standard deviation, you have to take a square root of the variance. One of the most prominent examples is multiplying a constant plus adding a constant, which is y equals mx plus b. In the linear transformation effect on mean and standard deviation. For mean is equal to y equals mx plus b, and the standard deviation, and that's equal to the variance of y is equal to m squared times by variance of x, and then you have to square root the variance, and that's equal to the standard deviation. Some common mistakes is that you'll forget to square root variance to find the standard deviation, and for expected value you have to add all the values. This can also be shown in variance because it's a summation formula as well.
For geometric, there are no fixed numbers of trials known, unlike the binomial setting. So the equation for geometric PDF would be the probability of failures to the power of the number of trials minus 1 times the probability of successes to the power of 1. So for example, there's a 25% chance of winning a game. What is the probability that the first success occurs on the 4th trial? So this means that x is 4 while the probability of success is 0.25. You apply the equation and you get 0.105. For geometric CDF, this is cumulative. For example, what is the probability of tossing 3 heads on a coin at most before tossing a tails? So since this is greater than or equal to 3, we would include the same equation as for the PDF, but we have to sum them all together, like do a summation. So this is when the probability x equals 3, 2, 1, we add it all together, but this is not our answer. We actually had to find the complement because we were trying to find something that is greater than and equal to, not less than.